So due to this wall deflection, so there is a low pressure region. So this sucks this supersonic flow so that it got deflected, and to adapt the pressure difference, so it creates the Mach wave collection of Mach waves that is called expansion fan. And as it is the Mach wave, the flow across this expansion fan is the isentropic. So there is no separate derivation to relate pressure, temperature, density and all. Already we derived the isentropic relations. Same thing we are going to use it. Okay, so there is no separation to relate pressure, temperature, density, etc. and all. But in the isentropic relation, we don't have the Mach number relation. Okay, so we didn't derive the derivation to relate Mach number across the Mach wave. So that only we are going to derive it here. So the definition is, whenever the flow is turned away from itself, but I will explain here. For example, here I have taken two different walls. So here, this is the original flow direction. But because of this ramp, that is wedge angle with the theta, the flow is turned into itself. For example, these are all the streamlines. Because of this ramp, the flow is turned into itself. That means this obstructs the flow, this turning flow. So there is an oblique shock wave formation. So the definition is, whenever the flow is turned into itself, there will be oblique shock. Okay. And here, if you see, this should be the original flow direction, but because of this deflection and low pressure, it is turned away from itself. So this creates expansion fan. Okay. So in the one word they will ask. So whenever the supersonic flow is turned into itself, it will form the oblique shock wave. Whenever the supersonic flow is turned away from itself, it will form the expansion fan. So depends upon this flow deflection direction only, you have to find whether there will be oblique shock or expansion fan. Is that clear? So here it is turned away from itself. So there is an expansion fan. Expansion fan contains n number of weak Mach waves. And usually you will measure the shock wave angle with respect to free stream. For example, this is the free stream direction and this is the Mach wave. Then this should be the Mach wave angle. Instead of here, they measured here because both are parallel, this wall and this flow. This may be the free stream for this wave and it deflects a little bit like this. But inside, we don't know how the flow changes, flow direction changes, etc. and all. So for simplification, so they are taking the downstream flow direction. So for the rearward, instead of measuring flow, that is angle between free stream, that is upstream and wave, here they are measuring wave on the downstream, mu2. So this flow is parallel to this wall, so they are measuring with respect to this wall. Is that clear? Because they know across the Mach wave, there is a small change in flow direction and the flow properties. The changes are negligible. So instead of taking upstream, they are taking downstream flow direction and wave. That they are measuring the wave angle. Is that clear? mu1, mu2. But general definition, always it has to be measured with respect to the free stream. But here the upstream properties are not known. So for simplification, they are measuring with respect to the downstream. Okay. So to derive the relation, so I am taking only one Mach wave from this expansion fan. So here the velocity is v, and there is a negligible change in flow direction d theta, and there is a small change in velocity dv. So with that, you are going to proceed further. Okay. So across the Mach wave, there is a small change in flow direction and small change in flow properties v plus dv. With that, they are proceeding further. So this is the Mach wave. This is the upstream property V, and the flow changes to d theta direction. So the velocity is increased to V plus dV. So only this portion I assumed here. Okay. And now they are drawing one normal line from the Mach wave. So because of this line, actually we are getting two right angle triangle. Actually, this is one right angle triangle. Okay, this is the first one. Then second one, the smaller one. Okay, so here we have two right angle triangle. So we know the Mach wave angle, which is measured with respect to the free stream flow, it is mu, and flow deflection angle is d theta. So the whole angle is mu plus d theta, and this is 90. Then in the right angle triangle, this angle we can measure. This is pi by 2 minus mu plus d theta. That only they are writing as pi by 2 minus mu minus d theta. Okay. So for this right angle triangle, we found all the angles. Here mu plus d theta, here 90, here it is pi by 2 minus mu plus d theta. Now they are going for this smaller right angle triangle. So this is 90 degree. Okay, only this right angle triangle you take it now. And this is mu. So this angle now we can find it. Okay, 90 minus mu. Is that clear? And this is a straight line. We know the angle of the straight line, it is pi. So this side we have pi by 2 minus mu. Then this side it should be pi by 2 plus mu. So that if you add both, you will get pi. Is that clear? Both right angle triangles. So here we have mu, here 90, then this should be pi by 2 minus mu. Okay, then for the straight line, so this side we have pi by 2 minus mu, then this side it will be pi by 2 plus mu. If you add both, you will get pi. So they are taking only this lower portion. Okay, so this is V component. This is V plus dV, this is d theta, and we have all the angles. With that, they are proceeding further. Actually, I said that the changes in the flow direction is negligible. So d theta is very small. Then in that case, sin theta is equal to d theta, cos theta is equal to 1. So now using that triangle, we are applying the law of sine. That is V plus dV divided by the opposite angle, sin pi by 2 plus mu. Then V divided by the opposite angle, sin pi by 2 minus mu minus d theta. Simplify, you will get this term. Actually, final equation, I need m2 in terms of m1 like that. Okay, I don't want other terms. So this velocity I can convert it later. And first I'm converting this tan mu into Mach number. Tan mu directly we don't have the formula, but we have the sin mu formula, Mach wave angle formula. And for this formula, if you draw the right angle triangle, then this will be the diagram. So here we have m, here we have 1, and this is mu. Once you know these two sides, this side can be found, then this will be root of m square minus 1. Now for this right angle triangle, we can find the tan mu, which is 1 divided by root of m square minus 1. So instead of this, I can substitute root of m square minus 1. So d theta is equal to root of m square minus 1 dv by v. So in that Mach wave, I have taken only one wave, right? Then for the complete expansion fan, I have to integrate it from theta 1 to theta 2. So both sides I am integrating. And here I have v term. This also I have to convert into Mach number. So I'm using these relations so that I'm converting dv by v is equal to this term. Now this is my final equation. Okay, and integration of this is here. Okay, integration of this root of m square minus 1, this term, it is given here, and for that they named it as Prandtl-Meyer function, gamma m they are calling that as Prandtl-Meyer function. Okay, so this side after integrating I'm having gamma m, and this side if you integrate you will get theta, then apply the limits theta 2 to theta 1, m2 to m1 something. So then if you apply you will get theta 2 minus theta 1, here gamma m2 minus gamma m1, and here the theta 2 minus theta 1, so the flow deflection angle, right? So this is the initial flow direction, then finally it will be turned parallel to this wall. So this complete angle is theta, it varies from theta 1 to theta 2. Okay, the flow direction initially it is theta 1, when it is changed to theta 2, the difference is theta. So directly you can take the difference. Okay, for example 20 degree means here they mention 20 minus 0, so difference is 20. So this is the final equation. Theta is equal to gamma of m2 minus gamma of m1. That's it. So theta is equal to gamma of m2 minus gamma of m1. For other properties, pressure, temperature and all, we will use the isentropic relation. There is no separate relation. Okay, explain how to find the Mach number. This is the Prandtl-Meyer function table that you can find it in the gas table book. And here Mach wave angle we used to mention mu, but there they mention as alpha. And here Prandtl-Meyer function we are mentioning as gamma m, they are mentioning as w or omega m. Okay, so this is Mach wave angle, this is Prandtl-Meyer function, and we are dealing with air, so we have to take gamma is equal to 1.4. This is for air. This you can neglect these two sides. Now this is the table. So normally in the problem they will give m1 and this theta. Okay, so once you know the m1, you have to go to this Prandtl-Meyer function table. For example, my m is 1.04. Using that you can find the corresponding gamma m value 0.351. So here it is 0.351. Assume this theta is 10 degree. So here it is 10. Then from this equation I can find the gamma m2. Okay, maybe some value you will get it. And once you know that gamma m2 value, for example, assume this is the gamma m2 value, then the reverse I can do. I can find the m2 using that. Okay, for example, m1 I have taken is 1.04. It is accelerated to 1.1. Like that, Mach number you have to find it. As I have taken the flat plate. Next, I have taken the diamond aerofoil. So in the supersonic aircraft, we won't use that blend nose aerofoil. We will use these diamond shaped aerofoils so that it will produce the weak oblique shock wave. If you use this, it will produce the strong bow shock, then drag will be more. Okay, this is at 0 degree angle of attack. Then second case, at some low angle of attack. I have 3 different cases. I'll explain what is this one by one. And always, for example, I'm taking flat plate at an angle and diamond shaped airfoil at an angle. So this is the free stream flow. It is parallel. Okay, and behind the model also again the flow will be parallel to the free stream. Okay, this you should be clear. This is the free stream flow. Over the model depends on it will be parallel to the wall. Again, it will be deflected parallel to the wall. That is free stream. Okay, always behind the model, the flow becomes parallel to the free stream. That is the first condition. With that we will proceed further. So here I have taken flat plate. So this is the free stream flow direction. And this is how the flow turns. It will be parallel to the wall, both sides. Again, it will become parallel to the free stream. Now, can you tell what type of wave I will get it from this corner? I have 4 corners here. 1, 2, 3, 4. Can you tell what type of wave I will get it here from this first corner? This is the flow deflection angle, flow direction. So from all 4 corners, I will get different wave as it is supersonic flow. Can you tell? whether you will get oblique shock or expansion fan or normal shock from this corner one.
Expansion fan.
Okay,
Expansion fan.
yeah, good. From here there will be expansion fan because this is the flow direction and it move away from itself. So there is expansion fan. Then corner 2.
Sir, oblique shock.
Okay, good. Okay. So here oblique shock because this is the flow direction. It is turned into itself. So oblique shock. Then corner 3.
Oblique
No.
shock.
Oblique shock.
Yeah, correct.
Oblique shock.
Oblique shock because this should be the flow direction. Again, it is turned into itself. So oblique shock. This is 4.
Expansion.
Expansion fan.
Yeah, good. Here it is expansion because this should be the flow direction, but it is turned away from itself. And mostly in this object, it will be like a mirror image. This one and this one will be like a mirror image. Okay, these two will be like a mirror image. These two like a mirror image. Whatever you are getting here, same thing will be here. Whatever you are getting here in the bottom, like a mirror image, you'll get it. Okay. Through this also you can cross check it. Okay, good. So here expansion, here oblique, here expansion. Okay, first case is okay. Now see the second case. And here this how the flow streamline will vary. And here I have 1, 2, 3, 4, 5, 6 corners. So here can you tell? Shit. Sorry. Mistakenly deleted it. 1, 2, 3, 4, 5, 6. Can you tell what type of wave you get here? The corner 1.
Oblique shock.
Oblique and one.
Oblique shock.
Oblique shock.
Okay, good. So here there will be an oblique shock because flow is turned into itself. Corner 2.
Expansion.
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 So here there will be expansion because this should be the flow direction. It move away from itself. And here,
Oblique.
Oblique.
okay. So here oblique, and here angle of attack is 0. Okay. So in the bottom also you'll get the mirror image. Oblique, expansion, oblique. Okay. Because see, this is the chord line, the red color line. It is aligned with the flow direction. So angle of attack is 0. So it will create the symmetrical wave pattern. Is that clear?
Yes, sir.
Okay. Now next see the. Okay. See here I explain. So oblique shock, expansion fan, again oblique shock, and you will get the mirror image as the angle of attack is 0. Then okay, next case. So this dotted yellow color line, is it visible?
Yes, sir.
Okay, so that is the flow direction, and this red color line is the chord line for this aerofoil. So this is my angle of attack, and the half-edge angle of this model is theta, and here the condition is alpha is less than theta. You can see that. Okay, the complete thing is theta, everywhere it is theta, half-edge angle, and now this is our alpha. So here condition is alpha is less than theta, and here also the flow will turn like this. And here can you tell what type of wave it is in the corner 1?
Oblique.
Oblique shock.
Okay, so here, good, here oblique. Because there is a small angle left here, right? Which is alpha minus theta minus alpha. This forms the ramp. So the flow is deflected with the same angle theta minus alpha. So oblique. In second corner,
Expansion.
Okay, so here expansion. Third,
Oblique.
Oblique.
okay, oblique, because this is the flow direction, it is turned into itself. And this is not the 0 degree angle of attack. So here in the bottom also you will get different wave pattern. It won't be symmetry. In the fourth,
Expansion.
Expansion.
Expansion, sir.
really,
Oblique.
Oblique shock.
Oblique.
Oblique
this is
shock.
this is the flow direction. It should be straight, but because of this wedge model, it is deflected like this. Okay, this is the flow direction. It is deflected like this into itself. So here oblique. Okay, the straight flow is turned into itself. So oblique here.
Expansion.
Expansion.
Yeah, here expansion, because it has to go like this, but it is deflected away from itself. And here
Oblique.
oblique. Okay, I already told you, like a mirror image. This and this mirror, this and this like a mirror image. Okay. Okay. So this how you will get it. Shock wave pattern and flow direction for this alpha less than theta cases. Same thing explained here. Oblique, expansion, oblique. Here oblique, expansion, oblique. Now second case. Here I have taken. Can you tell what is alpha here? So this is theta.
Zero.
Huh?
Sir, the angle between the green line and the chord line.
What is it? Alpha.
Theta, sir.
Yeah. Good.
Theta.
Yeah. It is the angle between green line and red line. It is correct. That we have taken as theta already. So previously I have taken alpha is 0. Okay. Always you have to measure alpha with respect to this chord line. Okay. Don't take these sides. It has to be measured with respect to this chord line. So here alpha is 0. Next case is alpha less than theta. Here alpha is equal to theta. Okay, so here this is the flow direction. Now, what is the way we will get it here? The one.
One will be oblique shock, sir.
So I couldn't hear. Sorry?
Where on it will be oblique shock, sir.
Oblique shock. Why oblique shock?
Because it's turning away from itself, sir.
Turn away means it should be expansion.
Normal expansion shock, sir.
Expansion. How expansion?
There won't be any shock.
Sir, at one there was
No shock.
Yeah.
It won't be any shock.
Yeah. Yeah. Correct. There is no shock waves. So this is the flow direction. Wall also in the same aligned with that flow direction. So there is no shock. Okay. It will be simply passing through this wall. If the Mach number is, for example, 2, here also Mach number just 2. Okay. There is no shock on this corner 1. Then corner 2.
Expansion.
Sir, expansion.
Yeah, good. And which student told that there is no shock? First one guy told.
sir.
Hmm?
I think. I think.
Aditya.
Aditya.
Yeah. Okay, good, good. Okay, so here there is no shock because the flow, there is no change in flow direction. And here expansion, and here
Sir, again.
again 3.
Oblique.
Sir, again expansion, I guess.
Here oblique, good. So oblique. This should be the flow direction, but it is again turned parallel to the free stream, so it is turned into itself. Oblique. Now fourth,
Oblique shock.
Oblique.
yeah, I told it is a mirror image. Oblique here,
Expansion
Expansion.
expansion here,
and oblique.
Oblique shock.
No.
oblique.
Normal there'll be
No,
no
no,
shock.
no
No
shock.
shock, sir. No shock, sir.
No shock. I told right, it's like a mirror image here and here, here and here. So here there is no shock. Okay, it is just straight. So this line and flow is in the same direction. There is no shock. Is it clear? This case, should I repeat?
Clear, sir.
Okay. So there is no shock here and here. Here it is always expansion. Here we have oblique like a mirror image. Then last case. Here what is the case I have taken? Previously I have taken
Greater than theta.
yeah, alpha greater than theta. So here this is the flow direction. Now here tell what is available here.
Sir,
Expansion, sir.
Good expansion here.
Expansion.
expansion, sir.
Okay, here also expansion here.
Oblique.
Oblique shock.
Oblique.
Okay, oblique. Here bottom
Oblique.
Oblique.
oblique. Here
Expansion.
here.
Expansion.
Expansion.
Okay, good. Yeah, this is correct. So expansion, expansion, oblique, oblique mirror, expansion, expansion mirror. Here it is always expansion. Okay. Yeah, very good. So now all the four cases I have shown here, and I'll tell some shortcut here. So here we are taking alpha greater than or equal to 0 degree. Okay, in all four cases, greater than or equal to 0. In all cases, you see, in the bottom, it is oblique. It's fixed. It won't vary. Okay, everywhere in the bottom, it is oblique. And everywhere in this corner, it is expansion. This won't vary. Whatever the angle, if you vary from 0 to all the positive, these three cases are fixed in all the cases. In the bottom oblique, in these two cases, expansion. Okay, and if this and actually this trailing edge portion, it is not required for us, because if you are finding forces acting on this model, we will find what is the pressure on this four surfaces. Okay, we don't measure what is the pressure behind this. Okay, so we don't care about this trailing edge shock. So even this one you can simplify like this without the trailing edge. Only these three corners are important. Is it clear?
Yes, sir.
Yes, sir.
Okay. 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 So even what is it? If you forgot how to mention this trailing edge, it is okay. It is not important. So as of now, these three are fixed. It is here. It is always oblique, and here it is always expansion. And only this will vary, depends upon the angle of attack. Okay, these two are fixed. Only three will vary. Okay, so here straight there is no shock. Here we have certain angle theta minus alpha, so there is oblique shock. Here it is more, so here it is expansion fan. That you have to find it, depends upon the flow deflection angle. Is that clear?
Yes.
Okay.
Yes,
Yes,
sir.
sir.
So without seeing anything, these three cases you can write it. Then by understanding that flow direction changes, you have to find the proper shock wave for this upper first corner itself. That's it. This is the first condition. And to solve the problem, first step you have to find the shock wave pattern on all the corner. Then you have to find deflection angle. Okay, with that only we have to find the remaining properties. For example, here I am taking Okay, assume theta is 10 degree. Okay, so here alpha is 0, theta is 10. Here alpha and theta both are 10. Assume here alpha is 5 degree, theta is 10 degree. Here assume alpha is 15, theta is 10. Okay, in all the case I am keeping theta is 10. So here I have 10 degree. This is the free stream flow direction, and the flow is turned parallel to that wall. Now what is the theta here? Flow deflection angle behind the first oblique shock.
So 10 degree.
Yeah, it is 10 degree. Okay. Okay, so here I have 10. Now this flow has to be again turned parallel to this wall. Now what is the theta here after the expansion fan?
Sir, 10.
Hmm?
20.
Yeah, good. 20. How 20?
If you draw a horizontal line, you'll get 10 on top, and it's symmetrical
Yeah.
bit.
Good. For example, here the angle is 10 degree. You draw an horizontal line. So both are opposite angle. And this another line parallel to this wall, if you draw, you know what is it? These two are horizontal line. This is a single line. Another 10 degree. Totally 20 degree. Okay. So if you draw a horizontal line, it will be easy for you. 10, 10, this is 10, 10. Okay. Is that clear? Should I repeat it? I think the image is very small. Should I explain separately?
Understood.
Okay. So here 10, then opposite angle also 10. And if we draw another one parallel line, then here another one 10, because this is a single line. This is also horizontal, this is also horizontal. So totally the deflection is 20 degree. So here 10 degree, and here 20 degree. As it is a 0 degree angle of attack, here also you will get same properties. Here also flow deflection will be 10, and after the expansion it will be 20. Is that clear?
Yes.
Okay. So second case, both are 10 degree. And what is the flow deflection angle here on this face? In this region, what is the flow deflection angle?
0.
0, sir.
Okay. 0.
Zero.
Here. Here.
Theta, sir. 10 degree.
10 degree.
20 degrees.
20. Just now we explained right here. Okay, same corner. It will be 20 degree. Okay. So here 0, here 20. Here the bottom. Here in this region. 20. Yeah. Okay, 20. Here.
0.
Hmm?
20.
Yeah, after the expansion. Just now
20.
explained, right? It is 20.
Yeah, 20.
Okay. Now this case, take alpha is 5, theta is 10 degree. Now in this region, what is the theta?
Five degrees.
Okay, 5. Because completely it is 10 degree. And this is the alpha, 5 degree. So this is the remaining one. Okay. So this remaining angle is 5 degree. Flow is deflected for this switch. Totally 10, alpha is 5, so remaining is 5 degree. For that the flow is deflected. Here, Sharima,
15 degrees.
here 15. How 15? This flow is
10 plus
parallel to
5.
this wall. This flow is parallel to this wall.
It's 10 degrees.
Why 10 degree?
10 degrees.
Side is no, so 15 degrees.
Hmm?
15.
Why 15?
On the left, theta plus 5 degree would be the angle.
I told right. This flow is parallel to this wall, and this flow is parallel to this wall.
20.
It is 20. Okay. Irrespective of the angle of attack, here it is 20. Okay. That is 2 theta. Okay. So always flow is parallel to these two walls. Everywhere it is parallel to the wall. It is 20. Okay. So here 20 degree. Okay, in this region, the bottom, this is the free stream flow direction, and it is deflected parallel to this wall. What is angle? This is the free stream direction. Above you said it is 5, then below. Is it so small? Then can I show this angle in different diagram? Is it visible?
Yes, sir. It's visible.
Even you can zoom right that page in your mobile.
Yes, sir.
Okay, then okay, you can zoom and tell what is the angle here. This straight line that is changed to parallel to this wall. What is the angle?
So 15.
Yeah, good. So above 5 degree and bottom it is changed to 10 plus 5, 15. In the bottom it is turned to 15 degree. Okay, the straight line turned parallel to this wall. That means angle between these two, 10 plus 5. Here, begin the expansion fan.
20 degrees.
It is constant 20. Okay, this case also over. Now come to the fourth one. Here, what is the flow deflection angle? Here, this is 10, this is 10, and I said angle of attack is 15 degree, this is 10 degree. That means the complete thing is 15 degree. Okay, from caught to free stream, it is 15. Wedge angle is 10. Now tell what is the flow deflection angle above this. Begin the first expansion fan.
15 degrees.
15 degree. Why 15 degree? This is the flow direction.
5.
So 5 degree.
Yeah. And this straight line is stand
5.
parallel to this upper wall. So here it is 5 degree. And same straight line In the bottom, it is turned parallel to this wall. Now remaining angle you have to find it. Sorry. So straight line to this wall you have to find it. What is the angle in the bottom? Straight line reflected parallel to this wall.
35.
How much? 35.
20 degree.
35.
Now 35. Straight line.
Sorry, 25. 25. 25, sir.
Yeah, good. 25.
25.
Yeah, correct. So angle between this straight line and this wall will be 10 degree, another one 10 degree and 5 degree, 25 degree. Good. And behind this expansion fan, it is same 20 degree, 20 degree. Is that clear?
Yes, sir.
So I will now I will tell the shortcut. Okay, instead of every time finding it. Shock wave, I told you, always here it will be oblique, always here it will be expansion. Okay, these two are fixed. Only here it will vary, depends upon the flow direction. If alpha is less than theta, there will be oblique. If alpha is equal to theta, then there is no shock. And if alpha is greater than theta, then there will be expansion. Okay, this way it will vary in this corner 1. Alpha is less than mean oblique. Alpha is equal to theta, there is no shock. Alpha is greater than theta, and there will be expansion. This is the shortcut for the wave pattern. Okay, these three are fixed. 1, 2, 3 corners are fixed. Only this corner will vary according to this. Is it clear?
Yes, sir.
Then if you see that, see the flow deflection angle, always behind this corner, it will be 2 theta. Okay, so behind this, the center corner, the flow deflection angle is always 2 theta. Okay, whatever the angle, whether it is 0 degree, 15 degree, 10 degree, whatever the angle, always in the after the center corner, the flow deflection angle is 2 theta, and in the upper surface, here the flow deflection angle will be the difference between theta and alpha. Okay, always in the upper surface, the flow deflection angle will be the difference in theta and alpha. In the bottom, if you take, it will be the sum of alpha plus theta. This shortcut you can remember it. So okay, in the center, always 2 theta. Upper, it will be the difference between alpha and theta. In the lower surface, it will be the sum of alpha and theta. Is that clear? We will check it. We
Yes,
found the value. We will check whether it is working or not. So upper I said difference between alpha and theta. Alpha is 0, theta is 10, the difference is 10. Okay. In the bottom it is alpha plus theta. 0 plus 10, it is 10 degree. And always in the behind the center corner, it is 2 theta. So it is 10 degree into 2, 20. Okay. Now go to this second one. Here it is alpha minus theta I said, that is difference. So alpha is 5, theta is 10, then the difference is 5. Okay. Is that clear?
Yes.
And the bottom I said it will be alpha plus theta. See, alpha is 5, theta is 10, it is 15. Okay, and behind that center corner it is 2 theta, 20 degree. And you take this now. Here also I said the difference between alpha and theta. The difference is 0. Okay, alpha is 10, theta also 10, the difference is 0. And in the bottom it is alpha plus theta, 10 plus 10 it is 20. Okay, and behind this expansion it is 2 theta to theta. Is it clear?
Yes, sir.
Then fourth case, here it is difference between alpha and theta. 15 minus 10, it is 5 degree. And here it is sum of alpha plus theta, 15 plus 10, it is 25 degree. Begin the expansion, it is 2 theta. That's it, shortcut. Okay. So regarding the wave, it is expansion. These two, it is, sorry, here it is oblique. These two, it is expansion. And this corner will vary according to this alpha. Smaller means oblique, equal means no shock, greater than means expansion. And flow deflection angle, here 2 theta, here 2 theta, here difference, here sum. That's it.